Today we prove the complex spectral theorem. Normal operators are exactly the operators that diagonalize using an orthonormal basis. Plane diagonalization allows a badly tilted basis. The spectral theorem gives a diagonal matrix without sacrificing orthogonality, a rare moment of civilization. Let V be a complex finite-dimensional inner product space, and let T be a linear operator on V. The theorem says, T is normal if and only if V has an orthonormal basis consisting of eigenvectors of T. Equivalently, the matrix of T is diagonal in some orthonormal basis. Not merely some basis. That adjective is doing actual labor. First, suppose there is an orthonormal basis of eigenvectors. Then T acts by scaling each basis vector. In that same orthonormal basis, the adjoint scales by the conjugate eigenvalues. So T star and T star T agree on every basis vector. Therefore they are the same operator. And T is normal. That proves the easy direction. Yes. Occasionally the easy direction is actually easy. Suspicious. But welcome. For the hard direction, suppose T is normal. We need to build an orthonormal eigenbasis. Over the complex numbers, every operator has an upper triangular matrix with respect to some orthonormal basis. This is sure triangularization. So choose an orthonormal basis where the matrix A of T is upper triangular. The goal is to prove this triangular matrix was secretly diagonal all along. That is the key technical move. Normality destroys the off-diagonal entries. The matrix wanted drama. Normality says no. From the previous episode, normality is equivalent to the length equality norm of Tx equals norm of T star x for every x. We apply this equality to the orthonormal basis vectors from the upper triangular matrix. Because the basis is orthonormal, squared lengths are just sums of squared absolute values of coordinates. Finally, a place where coordinates behave. The matrix of T star is the conjugate transpose of matrix A. So the first column of a star is the conjugate of the first row of matrix A. Now use norm equality on E1. The vector T(E1) only sees the first diagonal entry, while T star E1 sees the whole first row. The two lengths must be equal, so the extra squared terms must add to 0. Hence every entry above the diagonal in the first row is 0. After the first row is cleaned, apply the same argument to E2. Now the first row interference is gone. Norm equality forces every entry above the diagonal in the second row to vanish too. Repeating this row by row kills all off-diagonal entries. Upper triangular plus normal is diagonal. A small massacre, but a clean one. The matrix of T is diagonal in the orthonormal basis from sure triangularization. A diagonal matrix means each basis vector is an eigenvector. And the basis was orthonormal from the beginning. That proves the complex spectral theorem. Normality is exactly the condition that lets complex operators diagonalize without ruining orthogonality. The proof used sure triangularization, the length characterization of normality, and one brutal row by row cleanup. Linear algebra. Housekeeping with eigenvalues. Next, we can use the spectral theorem to understand special classes like self-adjoint, unitary, and positive operators.